Okay, last week I already gave the introduction for, last week we finished hypothesis testing for one parameter, and I hope you have good practice on that. This is once a week class, but I hope you don't study only once a week because you will have very hard time to catch up, as you can see from the number of students who actually left in this class. And of those, actually only half currently passing, by the way. No, this class is not easy, and some students ask me, Thomas, what happened to the rest of the class? I say, well, that's my question to them. I mean, you asked wrong person. But since the beginning of this semester, I already said that first, this class is actually best studied if you actually attend the class every day. So the best choice is like four times a week class. Now, I think at East LA College, they have only twice a week, and that's actually your second best option, and the best option available at East LA College. Now, studying once a week, like in my class, is not something I recommend, except when you are someone who can really manage your time. Okay, now, and the way I set it up also, I make it in a way that you don't need to attend the class, but the recording is available for you that you can review. You don't have to watch all 4 or 5 hours all the way in one day, but you can break it up into twice a week, right? So even though it is once a week class, but you can make it like you are studying twice a week or 3 times a week or 4 times, but you need to practice. You need to practice, okay? Not doing your practice like, how to say that? I can do all the lectures, but they will never get to your subconscious or really know how to do it until you practice to do it yourself, okay? Yeah, nobody learn how to play basketball by just watching. Nobody learn how to swim by just watching or take the theory. Okay, you need to practice, right? And now, likewise, especially because this is an applicable course, then you need to practice. Okay, now make sure you practice on that chapter 8 first before you start on this one, because my assumption is you already get used to the 6 steps that I provided before. Okay, now and then in this chapter 9, you will see modifications. Okay, now we will do in this order. Chapter 9, we will work on it out in this order: 9.2, and then 9.3, and then 9.1. Okay, now I follow the order of teaching confidence interval according to the traditional way of teaching confidence interval. We always start from mu, and then teaching p, and then sigma squared. Okay, confidence interval for population mean, and then population proportion, and then variance. Now then hypothesis testing on one parameter, it will also be from mu, and then p, and then sigma squared, right? Now, hypothesis testing for 2 parameters also follow the same ordering, okay? Even though I will not cover the last case. Okay, that's why I do it this way. Central limit theorem, which is the foundation of our confidence interval. Therefore, hypothesis testing are actually based on the mean, not on proportion. Yes.
Isn't there also not just sigma squared, but also just sigma?
Oh, that's actually part of that.
Okay.
That's actually part of that. The confidence interval actually first developed for sigma squared. Now, if you remember, I said in my lecture that the sigma squared is not well targeted by sample variance. Okay. Now the thing is sample standard deviation is not converging to the population variance that well. So the confidence interval that was developed actually was originally developed only for this case, only for that. And even that, it is done in a very, very strict situation that the underlying population has to be strictly normal. It has to be normal. And there are times that even though we have a very good circumstance that the sample standard deviation still do not target the population standard deviation that well. Yeah, okay. So what you said is true, but it's actually not a direct causation. It's more into like, oh, if so, then we can do the square root from there like that,
Okay.
Now, so I hope that explains why I always do it in this order. Okay, why I always do mu first while our textbook do proportion. Well, because the foundation of what we do here is actually central limit theorem. And central limit theorem actually talks about population mean and sampling mean and sample mean distribution. Okay, and population proportion is actually the result of that. Okay, so the mu is the one causing p, not p causing mu. Okay, well, anyway, that's the ordering. Well, it's too late if right now you want to, if you say, Thomas, why it has to be different from the textbook? It's too bad. We already did that since chapter 7, chapter 8. Now chapter 9 is just a continuation. Okay, now the first case we will do in this chapter 9 is hypothesis testing on two population means, independent case. The modification will happen in step 2 and 3 and 4 of those 6 steps. Okay, now we are comparing not a mean mu to a certain number like what we did in chapter 8. That's not what we do right now, but we are comparing the mu from two populations using the samples. The sample means from two sample means that come from two populations to judge, to measure, to compare the population mean. Okay, so in the hypothesis, you will see we have mu1 compared to mu2. Okay, but the rule that null hypothesis inequality contains equal sign and alternate hypothesis contains does not contain equal sign. Now, once we have this mu1 compared to mu2, we will modify that such that the other side we have constant. Okay, by subtracting mu2 both sides. Now, how about test statistic? Now, because we do not have the population variance, we will use sample variance. Therefore, the test statistic we use is t. Okay, now the p-value just follow up from the test statistic, because test statistic is t, then the p-value also will be t-CDF. Now we will do examples, of course, to put this all into practice. Now, after I'm done with these 3 examples, then I will go back to this test statistic to explain the theoretical foundation for that, which I think not being well provided even in our textbook. Let's start. Okay. I pick questions from our textbook. From my lecture videos, I believe I provide examples from questions that I get from internet from other university. And if you go to the announcement discussion board today, let's see. If you go to the discussion board today, you will see me giving on the discussion board today. I gave a handout, hypothesis testing procedure 2. Yeah, those are problems that I get from other universities. In fact, I get from at least 5 or 6 different universities. Okay, problem number 1 to problem number 7, I think are one parameter, and then starting from problem number 9 is 2 parameters. And those are this. I actually went over that in my video. As I remember, I went over that in my video. Okay, my lecture video. Those are the one I went over. Okay. Anyway, go back to our notes. So now I get problems from our textbook. Okay. Now, data set 26, collar weights and volumes in Appendix B includes Appendix B in our textbook, by the way. Includes the weights of contents of cans, Diet Coke, and compared to regular Coke. Now, let's list them in columns. So let's say the first one is Diet Coke, and then the second one is regular. Now, the first one, the diet, let me call that N1. The sample size is 36. The sample mean is 0.78479. And the sample standard deviation of these 36 samples is 0.00439 pounds. While the regular Coke, the sample size also 36. The sample mean is 0.81682, and sample standard deviation for the regular Coke 0.00751. Now, part A, which is that's what I will do. I will not do hypothesis. I will not do confidence interval for the difference of 2 parameters. I will not do that, but that's actually not too hard. The harder one is actually the hypothesis testing. So let's see. Part A, the alpha is 0.05. That's the significance level. Then test the claim that the claim is given to us explicitly. Test the claim that the contents of cans of Diet Coke have weights with a mean that is less than the mean for regular Coke. Hypothesis. We have null hypothesis, alternate hypothesis, and according to the claim, it means the first group, the mu1, the population mean for the first group, the diet one, is less than the mean for the second group, the regular one. Okay, now therefore the null hypothesis will be mu1 greater equals to mu2. Now again, our textbook would have used null hypothesis mu1 equals to mu2. If you do so, that's fine. Okay, if that's what you prefer to follow, that's fine. I'm totally okay with that. Now then, because we don't have constant to compare, then we subtract mu2 both sides of the inequality such that we get mu1 minus mu2 is greater or equals to 0. Mu1 minus mu2 is less than 0. Now from there, we see that the claim is in the alternate hypothesis, and it is a left tail. Now then, step 3, how about the test statistic? Let me get myself some space. The t is x bar 1, 0.78479 minus x bar 2. I think I should read it as x1 bar, x2 bar, 0.81682 minus mu1 minus mu2, which is 0. Remember, mu1 minus mu2 always come from the constant from the null hypothesis. Let's go back to the notation here. You see, this is a test statistic. Okay, T is the difference of the sample means minus the difference of the claim population mean in null hypothesis. Okay, over divided by the square root of sample variance of the first group. Don't forget to square it because that number is sample standard deviation divided by sample size of the first group plus standard deviation from the second group being squared to make it variance divided by sample size from the second group, which happens to be the same, also 36. Okay, now then we use our calculator to compute this. Now I want you to practice to compute this using your calculator though. Okay, I will show you two different methods to do that. The first one to compute that as is. Okay, so we will punch this number into our calculator, how to punch it to our calculator. Hold on. By the way, I'm recording this, right? Let me check.
Yeah, it's recording.
Okay, now, so we will punch the numerator, use parentheses, okay, always, okay, 0.78479 subtracted by 0.81682, close parenthesis. So remember, it's numerator divided by denominator, right? But the numerator has two terms, use parentheses for that. Divided by, now the denominator has only one term, all of them inside the square root. In other words, the square root in this case will also act as a grouping symbol. Okay, so you see that what I punch after this are all inside square root. Okay, 0.00439 squared over 36. That's the first term inside the square root, plus 0.00751 squared over 36. That's the second term inside the square root. And then I press enter, that's the number. Oh, wow, negative 22 something. Negative 22.09225. Negative 22.09225. Now, that's the first method. That's the first method to compute test statistic. Okay, now let me go on to step 4 first. Let me go on to step 4. Now, once you're done with that, then let's go on to step 4, the p-value. The p-value. Now, this is a t distribution, and the test is a left tail test. Negative 22.09225. And we want to check the left tail. So p-value will be TCDF. The lower bound is negative infinity. The upper bound is negative 22.09225. And the degree of freedom is 35. Now this 35, degree of freedom 35, is this degree of freedom is the minimum, the smaller of those two degree of freedom. Okay, degree of freedom for the first group is 35. The first group is 35. Degree of freedom for the second group is also 35. So they happen to be the same. We will use the smaller of those two, which happens to be the same also. Okay, now this is a conservative degree of freedom. Basically, we play safe. Now, the actual formula for degree of freedom is very complicated. I don't even remember that. To be honest with you, I don't remember the formula. The actual, let me write it here. The actual formula for degree of freedom in this case is very complicated. Let me see if I have that with me. I need to look for it in our. Oh, you know what? I remember. I think I have it somewhere. Give me a second. Not this one. 17. Let me see. I remember I actually did it somewhere. This one here. This is the formula. I don't even remember it. I mean, I don't use it. Where did I put your notes? Here. Yeah, so this is the formula. It's very, very complicated. Very, very complicated. Okay. Now, the thing is later on when I show you how to do this with calculator, then our calculator will actually use that formula. Okay, our calculator will use that formula. Well, it's calculator anyway, and they program it well. Now, so let's find out what our calculators say about this. Then let me move it here. So distribution TCDF negative E99, the upper bound is negative 22.09225, and we will use degree of freedom 35. The answer is 0, which I expect. Remember I said that when we have standard normal distribution, when we have standard normal distribution, which is very similar to T distribution. Now the area to the right of 10, the C-score is 10, the area to the right of 10, the area is practically 0, not precisely 0, but it's so small to the 17th decimal places already, or even more. Now to the left of negative 10, the area is also approximately 0 already. Okay, now imagine if you change that negative 10 even further to negative 22. So the tail is even smaller, right? It's so small such that even our calculator does not even want to compute it anymore. It just gives us 0. Okay, sometimes it still gives us some number, right? So let's say let me change the number a little bit. Okay, suppose I change that TCDF. Okay, and I change this to, let's say, -5. Notice that it still gives us some number. Like this is 8 at the 6th decimal place, right? Okay, if I make that instead of 5, let me make it -7, for example. It's small, but it still gives us some number. Okay, this is 1.9, so 0.0000000019. So 7 zeros after decimal place, 7 zeros after decimal point, and then 19 something. That's what that number represents. Okay. If I make it, let's say, -10, I believe it still gives us some number. Yeah, it still gives us some number, right? Okay, -22 is just like, no, it won't happen. It won't happen. In the sense that to claim, to say that given these are the statistic, right? Given these are the statistic, only people not in their right mind will say that the content of Diet Coke is not less than regular Coke. Okay, no, under no situation, basically. The P, I should say that the probabilities is there, but the probability is so small such that the probability that I actually get hit by thunder, I should say by lightning today, is actually still greater than that. Okay, well, the probability of every event, even though theoretically it's 0, but it's actually still possible. Will the sun rise at the west tomorrow? Maybe, because it's not happening yet, right? Okay, but what's the chance? We never know. Somebody will say, we will never know. Okay, I understand, we'll never know, but will you bet on that? Will you bet $1, $2, $3? Once you start putting money, then you start seeing the true face of that person's mind, instead of just being argumentative. Argumentative is like this. I get this question a lot every semester, and including in statistics class. Thomas, my average now, just for example, Thomas, my average right now is 30%. Okay. Do you think I have a chance to pass the class? And my answer, I don't need to think hard. I would just say, yes, you have a chance to pass the class. Okay. But I think the better question is, what's the probability? Okay, for somebody who has averaged 30% right now, to pass the class, you need to score 103 or 100, let's say 105% for my test 4 and test 5. For my test 4 and test 5, that person need to score 105% approximately on both of them. Okay, is it possible? That's possible. What is the probability? Near 0. Will you bet on it? But Thomas, that's possible, right? Yeah, that's possible. I mean, well, I will take the chance, whatever small it is. Well, to be honest with you, that's what I said to that person. To be honest with you, at this point, you cannot drop anyway, so don't worry about it. Okay, just do your best. But to say that you have a chance, it depends on what you mean by you have a chance. Simply because it never happened yet, and therefore we don't know, doesn't mean it will happen. Okay, I will not bet on it. But if somebody have average, let's say 90%, okay, 90%, and that person asks me, Thomas, do I have a chance to pass the class? Yes, your chance to pass the class is very high, extremely high. Okay, will you bet on that, Thomas? Yes, I'm willing to bet on that. Okay, if you just need to pass with a C, while your average right now is 90, yes, I'm willing to bet on that. I mean, I'm willing to bet my house on that. Okay. But no, not when it is 30%. When we say, oh, but Thomas, there's a probability, right? Yes, the probability is there, but the question is not is it possible? The question is, will you bet on that probability? If your answer is no, then stop talking about probability. Okay, we use probability to bet, but if you will not bet anyway, what for? Okay, that's just a figure of speech, though. Yes, Olivia.
But doesn't it also like matter like how much the final is worth? Because if someone has like a 90%, but like if the finals, like 2 last tests are like worth like a lot and then they bomb them.
Yes, the thing is, what is the probability they bomb that?
Very like low.
Right. So you see, like if somebody already up to test 3, which is at this point is 55% of the course up to test 3.
Yeah.
Is 55% of the course, and that person have average of 90. Okay, then suppose that person's test 4 and final, that person bomb it. Do you want to give me a number how they bomb it?
Let's say they get like a 43%.
Okay, let's say 43%. Okay, now of course we still question though, how can somebody who already get 90% in test 1, 2, 3 suddenly bomb that to 43? Okay, that's conditional probability.
Yeah.
Right. Okay, the probability is so small, right? But even in that case, I think this person still pass. I think this person still pass. Let's take a look. Okay, 55 times 90 plus 45 times 43 divided by 100. I think this person still pass, but let's see. Let me get my calculator. So 90 times 55 plus 45 times 43 divided by 100. See, that person's average is still 68.85. My passing is 68.
Okay.
Right? Okay.
Yeah.
So yes, that person may bomb it. Okay, that person may bomb it, but what is the probability that person bomb it? And the thing is, like for that person to bomb it to 43% average for test 4 and final means that person need to bomb it twice. Like this person did very well 3 times back to back. What is the probability that person bomb it 2 times back to back after that?
Pretty low.
Right?
Yeah.
Okay. So that's why I'm willing to bet my house on that. I mean, it's no, not only house. I can bet my wife on that too. I'm kidding. It's like if I know I'm gonna win and I will gain another one person, another one soulmate. Right? Okay.
Yeah.
Now see it from positive way. That's figure of speech. Okay. It's like I have so much confidence in that. Right. So no, it's very unlikely. Of course, in reality, I will not bet anybody. Right.
Yeah.
But if that person is willing to bet take my house for a bet, I will bet my house.
Okay.
You know. Now, how about if somebody get average 80? So instead of 90, does that person have a chance to pass the class? Of course, that person is currently passing. Does that person have a chance to fail the class, Thomas? Yes. Will you bet on that person passing the class? I will still bet it, but it will be quite measured.
Yeah, you wouldn't bet your wife.
Yeah, I will not bet other people. I may bet $100. Okay. Yeah, but not my car.
Yeah.
You know, something that I can bet if I lose it, I will just say, oh well, I will bet another thing. Right? It's just like I will not lose my living because of that. But it's so it's conditional probability coming to that now. So coming back to this, like even though you see the sample mean only off by how many pounds? It's like less than 0.04 pounds approximately, right? The difference is less than 0.04 pounds, but the p-value is already 0, which means we will reject null hypothesis in our informal conclusion. And then step 6 conclusion. At 5% significance level, there is sufficient evidence to support the claim that copy paste this thing. Okay. Unfortunately, in your test, you cannot do this, unless you use software also when you do your test. But basically, you need to copy paste that, whatever the claim you have there. Okay. Now, so this is the procedure, the 6 steps. And you see the one in which you will use calculator are actually step number 3 and step number 4. Now I will show you how to use calculator to get that number 3 and number 4. To get that number 3 and number 4. So in your test later on, when in the actual test, you still need to show me these 6 steps. You still need to write the formula. You still need to write the calculator notation. However, you can use calculator to compute. You go to test to sample t-test. Okay, this is a 2 sample t-test. Now then you input your statistic. Where's my statistic? Up here. Input the stats. X1 bar is 0.78479. Sample standard deviation for the first group 0.00439. Sample size 36. X2 bar 0.81682. S2 0.00751. Sample size 36. And we are doing less than in the alternate hypothesis. Now pooled, always say no. Calculate. Under what situation we do pooled? We will say pooled if we assume the standard deviations are the same. Okay, we don't have that assumption. Now, so let me screenshot and put the result here next to it so that you can see. Maybe I put it here. Now, okay, so you see that our t-score is the same, right? Our t-score is the same. Our p-value also happen to be the same. It happens to be the same, okay? But what I want to point out is that's because the t-score in step 3, the test statistics is so small such that for whatever degree of freedom, the p-value will be 0. But our degree of freedom is 35. The actual degree of freedom is this. That's the actual degree of freedom. Now, the reason they get this number is because they use this formula. Okay. So suppose let's say the t-score is only -2.09, let's say. Then the p-value will be slightly different. It will be off to, let's say, at the 3rd decimal place. But the 3rd decimal place means one number and the second 2 number after decimal point will be the same. In other words, we will still come up with the same result. Okay, when it comes to the p-value. So how to say that better? I want to say that your p-value will be the same. It will be 0 point something something, and it will be different starting from the third decimal place, maybe. Okay, starting from the third decimal place. Now, then what happened is, even though our p-value based on this conservative degree of freedom is different from the p-value we get from calculator because they use different degree of freedom. However, the difference of p-value is so small such that we will come up to the same informal conclusion and therefore conclusion anyway. Okay, it's like this. It's like this. Suppose you date a guy or a girl for already 7 years and you are about to get married. Let's say you're about to get married. Will you break up with that person, either that's a guy or that girl, because one time that person was late for 2 minutes?
No.
No, right? That's ridiculous. That's ridiculous. Nobody will do so. Why? Your sample size is already so big. You already basically make your decision that, yes, this is the guy, this is a girl for me. And you change your decision because 2 minutes late without asking why. I mean, at least ask why. Right? At least ask why. And to be honest with you, I will not even ask why. Hey, come on, 2 minutes. Okay, that's the time I go pee. Right? It's just be reasonable. However important that situation is, like 2 minutes late, no, I will not blame that person. Consider me bad luck. Okay, if I need something and I need it, it happens that the deadline 2 minutes ago and she came late, but I will not break up with that girl simply because of that. So that's the influence of statistic. So we do apply statistic in our daily life. We just never quantified that. What statistic trying to do for us is to quantify how reasonable we make such decision. Okay. Now, of course, then to be honest with you, we are Indonesian. Me and my wife are Indonesian. So in Indonesia, we have something called rubber clock. Rubber clock. Most Indonesians, I should not say all, most Indonesians actually subscribe to this philosophy. What is rubber clock? Rubber clock is like, when I say 7 o'clock, it may mean 7:15, it may mean 7:30. When I say, oh, let's meet at 7 o'clock, we may end up meeting at 8 o'clock. That's rubber clock. Means you can always pull it, you can always stretch that. Now, so I had that kind of mindset when I was in middle school. When I start to get to high school, I start to hate it, especially after I moved to America. When I moved to the United States 20-something years ago, I noticed that everybody respect each other's time. So it's like, it's not about me being disciplined only. It's about me respecting somebody else's time. So when I make appointment at, let's say 8 o'clock, then I'm supposed to be ready for that person by 8 o'clock, not at 8 o'clock, by 8 o'clock. Let's say 7:55, I'm already ready. If I say, well, I will pick you up at 8 o'clock, then 7:55, maybe I'll be there already. Okay, that's what it means. That's what it means. So when I start dating with my wife, my ex-girlfriend, okay, the first couple months, she always late by at least 1 hour. She always late by at least 1 hour until we get married. So one thing I promised her when we get married is, you know what, I marry you anyway, even though you have that habit of rubber clock. Okay, and instead of still asking you to change, that would be nice if you can change, but I will take it as like, hey, you know what, I married this girl. Okay, call that a cost. Okay, am I willing to pay for that? I don't mind. I don't mind. Okay, so don't expect her to be on time, and therefore every time I need to bring her with me, don't expect us to be on time. And every time we make appointment with somebody else, like let's say we have dinner with our friends, I will say, hey, you know what time we're going to meet? 8 o'clock. Okay, I will tell my wife at 7 o'clock. That way, then she will adjust. Now, recently, actually, after 2 years of getting married, she start to adjust and start to see how people actually respect each other's time. It's not about that how busy we are. It's also about how much respect we give to that person. That's appropriate way. That's the appropriate way. I'm glad that she actually changed, though. I'm glad that she actually changed. But even if she doesn't change, hey, you know what? We are married. The damage already done. I still love her. Okay. Well, anyway, let's go on date number 13. Are male professors and female professors rated differently? Use alpha 5% to test the claim that 2 samples of course evaluation scores are from population with the same mean. Claim. Two samples of course evaluation scores are from the populations with the same mean. Now let's organize the informations. The female professors, sample size 40, let me call that the first group. Sample mean 3.79 and sample standard deviation 0.51. For male professors, sample size 53, sample mean 4.01 and sample standard deviation 0.53. Step 2. So the word is they come from population with the same mean. So that the hypothesis, that will go to the null hypothesis. That will go to the null hypothesis. Why? Because it's the same mean, right? The mean for the first group is equals to the second group. That's the claim, right? That's the claim. So the alternative hypothesis, then they are different. Notice that the because the claim has no direction as which one is more, which one is less, it's just the same mean. Therefore, the alternate hypothesis will be two-tailed, okay, not one-tailed. Even though you see there is a tendency, people then say, oh, you know what, male professors is rated better compared to female, right? Okay, but that's not what is claimed though. That's not what is claimed. What is claimed is, are they the same mean or different mean? Are they rated differently or similarly? Okay. And I need to modify this such that I have constant on the other side. Then I subtract by mu2 both sides. I get equals to 0 and not equals to 0. Now the claim is here. Okay, and then this is a two-tail. Oh, you know what? Now I remember. I need to go back to the previous question. Let me go back to the previous question. I'm missing one little part here. Your extra credit part. Remember, for step 4, how to find the critical value. Yeah, how to find the critical value. Alpha is 0.05. So the alpha is 0.05. This is the T critical. So the T critical is inverse T, area to the left 0.05, degree of freedom 35. Okay, now then you use your calculator to compute that. Give me a second. I use my handheld calculator to compute that. I get negative 1.68957, while the test statistic is very far to the left, negative 22 something. Okay, that's why we reject null hypothesis. Okay, now like what I said, in your test 4 later on, I want you to use the 6 steps procedure, but if you want to have one extra point for every hypothesis testing, then give me the critical value. Okay, but you need to sketch the density curve, give me the calculator notation and the result from calculator. You need to give me those 3. Okay, don't just tell me, oh, critical value, bang, like that. No, no, no. I need to give me reason that you didn't just get it from somebody else. Okay, you get it from calculator, but you know what to punch in. How do I know you know what to punch in? You give me the coding. Okay, and you give me the picture here to show how you get that coding. Okay, let's go to step 3 here. Step 3, test statistic. I really thought that letting students having open book tests will help their grade. It turns out it doesn't. It doesn't. I already tried that since last fall. It doesn't help. Doesn't help. So there's a chance that next semester I will not let students to use open notes anymore. Maybe that's what makes them study ahead, because I saw some students actually study during the test instead, and they run out of time at the end. This is 0.51 squared over 40 plus 0.53 squared over 53. Now, instead of punching all those in, which you can if you want to, that's fine. I give you an alternative. You still need to write down the formula though. Okay, you still need to write down the formula. But what you can do is you punch all these numbers and do the hypothesis test on your calculator. Okay, now you know if you use calculator, then it will give you test statistic and p-value. Remember that? Okay, you still need to write a formula for me here, like this formula. I still need you to write it for me. Okay, but how you get that number, I will never know how you use your calculator, right? So just use your calculator. So x1 bar is that sample standard deviation for the first group is 0.51. Sample size is 40 for the first group. The second group, x2 bar is 4.01. Sample standard deviation 0.53. Sample size 53. And we are testing two-tail not equal to, and then null not pulled, and calculate. Done. So you will have these on your calculator, right? Let me screenshot that to help. Then you give me that number here. This is negative 2.02505. You see what I mean? Okay. I will not know if you actually use your calculator to compute this to get this. What I know is as long as you write this down, you know how to get that one. That's what I thought. Okay. But instead of punching so many things into your calculator, okay, why don't we just put it into the test, right? To put that into a calculator test statistic thingy. And then actually buy one, get one free. Why? Because after this, when I compute my p-value, I will get my p-value also from that screen. Okay, it's two-tail This is negative 2.02505. We need the area to the left, but double it because it's two-tailed. So the p-value will be 2 times TCDF. Okay, negative 2.02505. I'm sorry, from negative E99. Negative E99 to negative 2.02505, degree of freedom 39. Right? Now let me use my calculator. Inverse T. No, not inverse T. My bad. Clear. How to get up. TCDF. TCDF, negative E99. The upper bound is negative 2.02505. Degree of freedom 39. Dung, dung, dung. So I get negative, I'm sorry, 0.02487. 2 times 0.02487. Now multiply that by 2. Multiply this by 2. 0.0497. 0.04975, which is less than 5%, right? Okay. Now notice that our p-value, because we use this degree of freedom, which is different from their degree of freedom, it results in different p-value, right? But notice that even though our p-value is different, we still come up with the same conclusion. Do you notice that? Both of them is less than 5%. Bit different, but same conclusion. Okay, so can I use this result from that screen to help us finding the p-value? No, we cannot, but we can use that as a guide. That, hey, you know what? My p-value will be slightly different because we use different degree of freedoms. Okay, but it will be slightly different. And if my first two decimal place match, I will be happy. It means I did it right. Okay, now the thing is in their situation, in our situation to be more precise, if I round it to 2 decimal places, it will be 0.05, right? That's why we don't round to 2 decimal places, round to 5 decimal places. Then we can see better. Now, then with this said, then step 5, informal conclusion. Reject null hypothesis. It's less than 5%. If I have to make decision, if I have to make conclusion at this point, then I will reject null hypothesis. Even though with that kind of p-value, it's too close to 5%, I will say, can I increase the sample size? Okay, can I increase the sample size? Why? It's too close, you know, it's too close. But if I have to make decision, then the decision will be reject null hypothesis. Okay, at 5% significance level, there is sufficient evidence actually insufficient evidence. No, you're right. I'm right. There's sufficient evidence to reject because it's our claim is null hypothesis, right? Our claim is null hypothesis. If the claim is null hypothesis, then we will try to reject we'll try to reject. Okay, and informal conclusions say that we will reject. So there is sufficient evidence to reject the claim. That then you copy paste whatever you have in the claim. Okay, unfortunately, again, next week when you take the test, you have to copy this down in writing, right? Now, how about the critical value just for our extra credit, let's say 4B critical value. In this case, it's actually critical values because it's two tails. We want 5% for each tail. So 0.025% each. Okay, 95% in the middle. So T critical will be inverse T plus minus. Inverse T, the area to the left, 0.975, degree of freedom, 39. Again, we are being conservative. So plus minus inverse T. Area to the left, 0.975, degree of freedom, 39. 2.022269 plus minus 2.02269. Let's see. You see our test statistic? It's slightly to the left of that. So let's say this is negative 2.02269. Our test statistic falls slightly to the left of that, very little to the left of that. But it's still already on the tail region, right? It's already in our tail region, slightly to the left of that. So we reject null hypothesis. Okay. Now let's do one more problem and then we take a short break. Number 15, again from our textbook. Are quarters now lighter? Weights of quarters are carefully considered in the design of vending machines that we have all come to know and love. Okay, the vending machines. And what happened is the following. We have the one pre-1964 quarters with sample size 40, the sample mean 6.19267, sample standard deviation is 0.08700. Now post 1964, sample size also 40, sample mean 5.63930, and sample standard deviation 0.06194. Okay, the alpha still 5%. So test the claim that the claim pre-1964 quarters have a mean weight that is greater than the mean weight of post 1964 quarters. Then step 2, hypothesis. Null hypothesis, alternate hypothesis, mu1 is greater than mu2. So the null hypothesis, mu1 less than equals to mu2, we need to modify this so that we have constant on the other side, mu1 minus mu2 less than equals to 0, mu1 minus mu2 greater than 0. Alternate hypothesis is the claim, and that's a right tail. So our test statistic T equals 6.19267 minus 5.63930 minus the difference of mu1, mu2 as claimed is 0 is divided by square root of 0.08700 squared over 40 plus 0.06194 squared over 40. Now, when I use my calculator, I will use test statistic part. That way, then, I just plug in the number once. I don't need to compute anything. I need to be too careful with the numbers when I plug it in with the notation. Yet I can get the test statistic and the approximate p-value later on. This is right tail, not pull, calculate. Oh, wow. The test statistic is way too high. So this is a clearly reject null hypothesis. So this is 32.77081. Okay, then the p-value will be, it's a right tail. So p-value, that's TCDF 32.77081 E99 degree freedom 39. Yeah, you see from the p-value here, that's to the power of negative 44. So even if we round it to 5 decimal places, that will be 0. Okay, but let's confirm with our calculator. TCDF 32.77081. The upper bound, make it very big number, degree freedom 39. Yeah, still, if we round it to 5 decimal places, that will be 0 anyway. Right, that's 2.689, 2.689 times 10 to the negative 30. That's approximately 0. Okay, again, where I said earlier, if we round to 2 decimal places, we should have the same value with the 2. If we round to 2 decimal places here, that will be the same to 2 decimal places there. In this case, both of them give us 0. Okay, now then, informal conclusion, reject null hypothesis. And then step 6, conclusion. At 5% significance level, there is sufficient evidence to support the claim that pre-1964 quarters have a mean weight that is greater than, let's see what's the formal wording, have a mean weight that is greater than the mean weight of post 1964 quarters. Okay, that's for this section. I try to do some problems more from there, also especially my handout. Okay, I will take a break in a couple minutes, but let's see, what is 9.3? 9.3 is hypothesis testing on 2 population means okay, but this is dependent case. To be more precise, sometimes, most of the time, they call that match pair. Match pair case. Okay, now the situation will be, the modification will be in step 2. In step 2, the null hypothesis, alternate hypothesis will be about mu1 not equal to, less than equal to, I'm sorry, not equal to, less than or greater than mu2. Just like in our previous case, we modified this to be, to have one side become 0 by subtracting both sides by mu2. Okay, but then we go on further because it's match pair. So what we will do, we will only see the average of the differences. We'll see the average of the differences. Okay, that's the modification. Now then, in step 3, when we do the test statistic, so this is for the hypothesis. For the test statistic, we will still use t value, okay? But on the top, we will have d bar minus mu d over sd over square root of n. Now, this is actually coming from what we learned in chapter 8, t equals to x bar minus mu over s over square root of n. The difference is we compute the average of the differences instead. Okay, those are the two modifications from what we learned before. Okay, now later on we will apply that to our case here. Okay, of course, when we come back, I will first explain what is the difference between independent case, the one we learned earlier, and dependent case or match pair, which is what we will do next. So right now it's 9:35, 9:36. Let's come back at 9:46. Okay, what happened with, what's the difference between independent and dependent case? For independent case, as you've seen before, independent case, that's what we saw in 9.2. That's when the sample comes from two different populations. So for example, the one we had was the one pre 1964 coin and post 1964, right? So if the coin already included here, it won't be included there. You see, it won't be. Or when we talk about the survey for male and female professors, right? Male and female professors. Those are from two different populations. Okay, now how about dependent case? That's 9.3, dependent case. Now you will see we can match them. Like for example, in this number 7 here, okay, in this number 7, we have 7 body temperatures, okay, but from 7 different subjects. 7 different subjects, okay, 7 different people, okay, but the same person measured, like the person number 1, object number 1, his or her body temperature is measured at 8 o'clock and the same person is measured at 12 o'clock. You see what I mean? Okay. So the second person measured at 8 o'clock and then at 12 o'clock. So that's what we call match pair. That's what we call dependent. So what happened is we are matching this number later on with this number. We will not match this number with this number, for example. No, we will not. Okay, why? Because it's the same person, right? We can match them. We can match them. So they come from the same population, but with different methods of measuring. Okay, like one different method is like one at 8 o'clock, the other one at 12 o'clock, or maybe measured at the same time, but using two different thermometers. You see what I mean? Okay, so the subject are the same, but the methods are different. Okay, we can match because they come from the same subject. Okay. We'll see more examples for that. Now, because of that, what we will do is we will find the differences which we call D and compute the D bar, the mean sample mean of the differences, the different sample, the mean differences from the sample, and standard deviations of the sample differences. Okay, we call that as sub D. We will do that. We will find the differences and perform hypothesis tests on one mu with sigma unknown. That's what we learned last week. Okay, so test the claim in part A. I use a 5% significant level to test the claim that there's no difference between body temperatures measured at 8 o'clock and at 12 o'clock. Okay, what we will do first, we will find the differences for each. We'll find the differences for each. Let's call this group 1 and this is group 2. Then the difference will be group 1 subtracted by group 2. Okay, and this will be negative 2.4, negative 1.4, negative 1, negative 0.8. Is it right? And negative 1.5, negative 1.5 again, and this is negative 1.8. Those are the differences. Now then, for us to find the D bar, we need to find the sum of D and the sum of D squared. You see what I mean? Now, after we find the sum of these, then we'll find the D bar and find the standard deviation of the variance of the differences, and from there we do the square root to get the standard deviation of those differences. Can you follow me? That's what I will do next. That's what I will do next. Okay. Now, because the process will be quite long, I will just do a little shortcut. And I think this is important for you to save your time during your tests. I will plug in numbers to our calculator. Okay, so let's see, or my list 1, 2, 3, or my list 1, 2, 3 is occupied here. So let's delete them first. Clear list. I will clear list 1, list 2, list 3. Am I sharing? Oh no, I'm sorry. I should share this one. I thought that you can see this. So let me do it again. I will input the value into list 1, 2, 3. Okay, now to clear the list, if you're still occupied, there are some data in there. To clear them, then you go stats, clear list. Okay, and suppose you want to clear list 1. This is list 1 here. Okay, so you go second, list 1, comma, list 2, comma, list 3. If you want to clear those 3 columns, you need 3 columns. Okay, now here's the thing. Then we will input the data. I hope you follow me. Follow me. even if I repeat this, I will repeat that only twice more from now. Okay. I don't want you to ask me that question in the next example. No, I want you to learn it now. Now, I will subtract the first list minus the second list to get the difference. Okay, so my first list will be the one from row number 1. The first data, 96.6, 97, then 97, 97.8, 97, 97.4, 96.6. So as you can see, we have 7 data, 7 subjects, right? Now I go to, after you enter that, you go to the second list, and you need to enter the data in the same order. Because remember, it's match pair, right? So this is 99, 98.4, 98, 98.6, 98.5, 98.9, 98.4. Okay, so I already insert the data, right? To input the data, I believe you have known how to do that already. We have done this for like 2 or 3 weeks. Yeah, we have done this for the last 2, at least the last 2 weeks, Input the data. Now, we go to list number 3, okay? But instead of computing the differences and put it in, we will ask the calculator to compute it for us. How to do so? You go up, you go to the header. So you see that the highlight is here. You go up. You see, now then you get to the header, L3, right? Now you will tell calculator to subtract from the first column minus the second column. So L1, follow me, minus L2. Are you okay? Then I will press enter. So the numbers you get here, they will fill it up for you. So the first one, negative 2.4, the second 1.4, right? The third one is negative 1. The fourth one, negative 0.8, negative 1.5, negative 1.5, negative 1.8. Now to find the sum of these squares, then you go to stats, calculate one var stats. And we will calculate list 3, the differences. Let me put it here. Now from there, you see the sum of these is written as sum of x's, negative 10.4. Sum of these squares is 17.1. Now what is d bar? Pretend that you compute it. Negative 10.4 over 7. That will be negative 1.48571. How about sample variance of the differences? Then, according to the formula, that will be 7 times 17.1 minus negative 10.4 squared over 7 times 6. Then use your calculator to compute 7 times 17.1 minus 10.6 squared. Even though that's negative, when you square it, becomes positive, right? Now then divide it by 7 times 6 is 42. So that's 0.17476. This is 0.17476. Now apply square root on this. That's 0.4180 what? 0.45, so 5. Now then you compare to what we have here. Something not right. Something not right. It's very different. Let me check my computation again. Did I punch anything wrong? Ah, I typed something wrong earlier. I typed it wrong here. It's supposed to be 10.4. Right? Okay, let me do it again. 7 times 17.1 minus 10.4 squared all over, 10.4. Delete square. It's then divided by 42, 27476. Now then you apply square root on that number. 0.52418. Does it match right now to 5 decimal places? The thing is, our calculator show you this, but our calculator cannot give you this. So basically you use this and apply the square root and use the result from your calculator to confirm. Okay, but notice that I play with my calculator to get these numbers. Okay, now then once we get these results, then we are ready to do hypothesis test. So step 1, claim. Step 1, claim. There is no difference between body temperatures measured at 8 a.m. and at 12 a.m. There is no difference, so they are the same. Between body temperatures measured at 8 a.m. and 12 a.m. That's the claim. Step 2, hypothesis. There's no difference. So mu1 equals to mu2. The complement, therefore, not equals to mu2. We need to modify. Null hypothesis is mu1 minus mu2 equals to 0. Alternate hypothesis is mu1 minus mu2 not equals to 0. Oh, but this is match pair. So mu d equals to 0 or mu d not equals to 0. The claim is with the null hypothesis. So later on we'll try to reject the claim. Okay, and from the alternate hypothesis we see that this is a two-tailed test. Now, if you want to skip this in your test, go ahead. Okay to skip in your test. Okay, then step 3, test statistic. T is equal to D bar. What is D bar again? Negative 10.4, as I remember. No, negative 1.48751. negative 1.48751, 571, sorry, 571 minus mu d, which is 0, as said in the null hypothesis, over sample standard deviation of the differences, that's 0.52418 over square root of 7. Okay. Now, again, you can use calculator to compute that. I mean, yeah, I think that's actually quite easy to compute. Negative 1.48571 divided by the parentheses of 5.52418 divided by square root of 7. Negative 7.49899. Negative 7.49899. That's the test statistic. Now, you can also use hypothesis testing part, t-test, right? Okay, you input the data. The mu naught is 0. X bar is, oh, they computed for us. S sub x, they computed for us. Sample size 7, they computed for us. And we are doing two-tailed tests. Now calculate. So this way, you still need to write the formula, the notation though. You still need to write. You still need to write this. You still need to write this. Okay, you still need to write this. Okay, but you know your answer here will be the same. Okay, but Thomas is actually quite different. The difference is because notice that we round it to 5 decimal places. They don't. They don't round it to 5 decimal places. They stop here. They stop there. So if you want to get a more appropriate result here, then what you do is when you do the test, the t-test, okay, truncate it here. Truncate that here. Negative 1.48571 only. And then the sample standard deviation of the differences, 0.521, 52418. That's what you enter. Then that's what you get. Okay, let me update it. Now, our p-value later on will be this. Okay, this will be our p-value later on. But at least you now know how to confirm your result, right? P-value 5% two-tail test. So this is negative 7.49899. Degree of freedom is 6. So p-value is TCDF negative E99 negative 7.49899, degree of freedom 6. That's equals to 0.00029. Okay, why? Because this guy here is actually 2.908 times 10 to the negative 4, which means the 2 here starts at the 4th decimal place. Okay, now notice that the p-value is much, much less than 5%, so we will reject null hypothesis. And therefore, the conclusion will be there is sufficient evidence to reject the claim. Why do we reject the claim? Because the claim is with the null hypothesis. At 5% significance level, there is sufficient evidence to reject the claim that there is no difference between body temperatures measured at 8 a.m. and 12 a.m. Now, for extra credit, for B, what is the critical value? It's two tails, that's critical values. 5% is the alpha, so 0.025 each tail, while the middle is 95%. Now, the critical values are these two numbers here. That's plus minus inverse t, area to the left 0.975, and degree of freedom 6. Using my calculator, inverse t, area to the left 0.975, degree of freedom 6. 2.44691. 2.44691. Okay, that's why you see that our test statistic is outside of that. Our test statistic is -7 something. This is -2.44. Our test statistic is -7. That's why we reject null hypothesis. Okay, so that's another reason we reject null hypothesis. But critical value method and p-value method always give us the same result. Okay, let's do the next example. This time, I want you to do me a favor. I want you to find those D's. Use your calculator. Okay, let's say this is the first group. Let's say this is X, this is Y. Then the difference will be X minus Y. Now, I want you to give me this difference, but first, input to your calculator. Okay, you need to clear lists first because your lists 1, 2, 3 are currently occupied, right? You need to clear lists first, and then input the data in that order to your list 1 and list 2, and then your list 3 will be the difference. Okay, now once you get those D's, then use one stat var to compute sum of D's and sum of D squared, and D bar and SD bar. Just look at the Look at your calculator to give me those numbers. In your real test, in your test next week, I will ask you to compute this. Okay, but for now, let me ask you if you know how to input the data and get this result for now. Okay, let me give you 5 minutes to do so. Right now it's 10:16. 2 minutes, 2 minutes, yeah, 5 minutes. So I will come back at 10:21. Okay, I hope you do what I told you. It's to make your life easy. Okay. I would like you to use calculator to help you speed up your computation. And so that's why earlier I asked you to do it on your own first. Okay. I have this case though. Actually, it happened from your class in your test 3. During your test 3, I knew one student because she asked me during the test, Thomas, how to use calculator to do the confidence interval again? It's like, what? You asked me that during the test? Why don't you practice? I don't have time. Okay, what makes you think you are the only person don't have time in this world? Oh, you know, and then I say, no, I cannot help you with that during the test. What you can do, you watch the video during the test. Of course, this person didn't have enough time because then she asked me, Thomas, do you remember which video is that? It's like, huh? It's like, even during that time, I wanted to get mad. I don't know how to get mad. So you know what I did? I was smiling. Good thing the video is not on, right? So you didn't, she didn't know that I was smiling. But what else do you want me to do but smile? It's like, I really want to say, I told you, right? Okay, if you don't want to study, okay, don't expect to pass the class, and why bother taking the test? Oh, you know, of course, that's not what I want. I want you to study, right? I want you to pass the class. But thinking that you can just take the test and suddenly something wrong with Thomas' mind and then he just passed you, it's like you really base your passing on a luck, right? Okay, is it possible to happen? Yeah, it may happen. Has that happened before? No, not in the last 20 years I'm teaching. So saying that it suddenly happened this semester and it happens to you, it's a big leap of faith. Oh, you learn statistics for what? So that you don't need to rely on faith, right? Oh. No, I'm telling you this not because I say, well, you are the one doing it. No, I'm saying that however good intention I have, you still need to do your part. Okay? Please, please, please. I want you to pass, but you still need to do your part. Okay? I still need to pass you when I have confidence that when I present you to the society, when I present you your grade, that's something I can be responsible on. So I plug in the numbers, make sure that you plug them in the same order. So you need to follow the list though. Okay, so number 7 is 69, that's right. And then 64, then 63.5, 66. So there are 10 data here. I am also a member of the SUM students group at East LA College Facebook page, and I have seen students complaining about their stats instructor, and I was one of them. I have students complaining about me, but they put it on public, and then when I respond, that person suddenly just becomes just took off. That person just become not a member anymore. He deleted his posting. But it's like, why this instructor always blaming it on students? No, I'm not blaming on all students. No, I'm blaming it to some students. Not all students behave like that person. Just like you in this class, I have some students actually doing very well, so well. Okay, too bad because of the student privacy, I cannot name them. But there are 2 students doing very, very well. I'm so happy for them. Okay, now the thing is why other students then cannot follow through. Okay, why other students cannot do, they cannot get what they get, right? That's so pity. That's so pity. You know, these students even say, oh, your test is straightforward, Thomas. It's to the point of boring. And the comment she made is like, your test score will be even more boring. It's just a lot of writing. I say, yeah, I agree with you, you know, but still I have to test it that way, right? Yeah, she is fine with that. It's just like, hey, there's no challenge at all. You make the test is so obvious, Thomas. Yeah, but the thing is, like, if you look at the average on Canvas, no, they are not that obvious for a lot of you. Now, I want my more students actually being successful like they do. Okay, I don't make my I don't try to make my test super hard to pass. No, if you just need a C, then as long as you study, memorize some problems, especially with the open book, supposed to be easy for you guys. L1 minus L2. So I input the data, L1 minus L2. I get those differences. Let me copy them down. Okay, because in my test, I will ask you to fill in the D's. So I borrow that here. And let me scroll down. Borrow that here. So that I don't need to keep on coding, looking at my calculator again. So this one is negative 0.5. This is 0, negative 2.5, negative 4. This is 1, negative 1.5, 0, negative 4, negative 1, 3. So those are the differences. Now, go back to my calculator. I go to stats, one var stats, compute on L3. Okay, so the sum of the data is negative 9.5. The sum of the squares is 51.75. The D bar is negative 0.95. And standard deviation of the differences will be 2.17881. Okay, at least you can get these 2 numbers from your calculator, right? Okay, now if I wanted you to compute, to show me the computation for D bar, then you say, okay, that will be the sum of these divided by the sample size. That's how we get negative 0.95 for the D bar. Now, how about sample variance for the differences? That will be 10 times 51.75 minus negative 95 squared over 10 times 9. That's 10 times 51.75 minus 9.5 squared divided by 10 times 9, that's 90. So 4.74722. 4.74722. Now then, standard deviation of the differences will be the square root of that. 2.17881. 2.17881. And you see that you can confirm that, right? Okay, at least you know that you get the right answer. That gives you more confidence to work on the problems after this. Then we start the hypothesis testing. What is the test? What is the claim? Claim. that there is no difference in heights. There is no difference in heights. Difference in heights between mothers and their first daughters. Oh, because this is a result from Francis Skelton. I think I will share this with my wife later on after class. Compared to most Indonesians, my height is actually above average, significantly above average. On the other hand, my wife's height is significantly below average, even compared to Indonesians female. So in America, if you see me walking with my wife, you'll be surprised that I'm actually married my friends usually say, joking of course, Thomas, how can you marry an underage? I say, no, she's not. She's actually only 1 year younger than me. But she does look like a teenage. You know, if you see her, she looks like a teenage. Her height is not even my shoulder. It's very short, very short. So she said that what happened to our daughter later on? Will she be that short? Okay, my son apparently follows me that he is actually taller, on the taller side. But we don't know yet about our daughter. We don't know. I said, well, it doesn't matter as long as they are healthy and happy, then that will be my pleasure already. That's my joy. Okay, so there's no difference in heights between mothers and their first daughter. So mu1 equals to mu2, right? Let me just go ahead with the modification later on. Then mu d equals to 0, right? Okay, mu1 not equals to mu2 because it's matched pair. Then we will measure the mu d, the average of the differences. Step 3, test statistic. T equals to d bar negative 0.95 minus mu d 0 over sample standard deviation of the differences. That's 2.17881 over square root of 10. What's that? Let me use calculator right away to compute using hypothesis testing, t-test. Okay, I put in a number. To make it more accurate, let me use the number I use, the 5 decimal places. So this is 2.17881 instead of that 10 decimal places. And it's a two-tail test. Okay, calculate, then screenshot. So during your test, you show me what I wrote in black, right? Okay, you don't need to show, you don't show me the calculated result. The calculated result only to help you confirming your answer. Okay, negative 1.37881. And then step 4, p-value. That's two-tail. This is negative 1.37881, but it will be two-tail. Okay, it will be two-tail. So p-value is 2 times t, CDF, negative E99, negative 1.37881, degree of freedom 9. That will be 2 times, let's use our calculator, TCDF, negative E99, that's the lower bound. The upper bound is negative 1.37881, degree of freedom 9. That's 2 times 0.100063. 0.100626 multiplied by 2, that will be 0.201252. Like if I make it only 5 decimal places, that's it. And then you see that my p-value is the same. Then I confirm. Okay, then I confirm. Yeah, this one also confirm, right? I actually took it from there. But let's see. To really confirm it, let's compute it. Negative 0.95 minus 0 divided by the quotient of 2.17881 divided by square root of 10. You see? Confirm, right? Oh, that's nice. Then go on with informal conclusion. That's greater than alpha. Fail to reject null hypothesis. And then step 6, conclusion. At alpha 5%, as I remember. Yeah. At alpha equals to 0.05. You can also say 5% significance level. There is insufficient evidence. There is. See, the claim is with the null hypothesis, right? There's no difference. So the claim is here, right? Okay. Now, so if the claim is with null hypothesis, we will try to reject, but then now we have insufficient evidence to do so. There is insufficient evidence to reject the claim that there is no difference in height between mothers and their first daughter. For extra credit, how about critical value? It's 2 tails. Hold on, the test earlier. It's 2 tail. I make a mistake here. This is a 2 tail. So see, I didn't check that. I believe I get the right answer, but I supposed to have the following. I need to correct this part. This is 2 times, it's 2 tail. The thing is it's 2 tail. So I had supposed to multiply it by 2. So it's 2 tail. 2 times T, C, D, F, negative E99 to negative 7.49899, degree of freedom 6. So TCDF, I forgot, I totally forgot to multiply by 2. Negative E99 and then negative 7.49899. Degree of freedom is 6. So this is what I get here is 2 times 4, 5. 0.000145. Right now, then when I multiply this by 2, that's 0.00029. Okay, so the actual TCDF that I get earlier is not 2.9 something. No, it's not. That's after I multiply by 2. Yeah, I keep on thinking that was one tail. Good thing I did number 2. Then I realized, oh, you know what? I forgot to multiply by 2 for that one. So this one here, 5%. So 95% in the middle, 2.5% each tail. Okay, so this negative critical value, the critical value is plus minus inverse T 0.975. That's the area to the left of these, the area to the left of that. And degree of freedom is 9 in this case. Inverse T, area to the left 0.975, degree of freedom 9. 2.26216. That's plus minus 2.26216. Okay. That's for the second example. Now the third example. From number 13, Friday the 13th, researchers collected data on numbers of hospital admissions resulting from motor vehicle crashes, and the results are given below for Friday the 6th and Friday the 13th of the same month. Okay, now the question is construct a 95% confidence interval. No, that's not what we will do. I can do it later. But what I want you to do is to test the claim at 5%. Test the claim that that's the claim. Okay, but of course I need to find the D's first, right? So let's say this is the X, this is the Y. I need to find the D's, and then from there find the sum of D's, the sum of D squared. And then we will just use calculator later on to find the D bar and standard deviation of the differences. Okay, I will just do it fast. Now then I use calculator, plug in numbers again. Stat, edit, notice that my list 1, 2, 3 are occupied, so I will clear them. Remember how to clear them. Go to stats, clear list, L1, L2, L3. Now then you check again, go to stat, edit. Now it's empty now, right? Now then We go to list 1. First number 9, and then 6, and then 11, and then 11, and then 3, and then 5. So there are 6 datas. And then L2, we have 13, we have 12, we have 14, we have 10, and then 4, and then 12. Wow. Get ready. There's a chance that they are actually affected. There's a chance that they are actually affected. Okay. Because from here you see, from all these numbers here, only this case where Friday the 13th, the number of hospitalization due to vehicle crashes is less. But for the rest, there are more. Right? You want to call that superstitious? I mean, I want to call that superstitious, right? I mean, nobody will call in sick simply because it's Friday the 13th. Is that right? Okay. But when we see this number here, it's kind of a bit scary though. Okay, let's see. L1 minus L2, L1 minus L2. Let me copy the number. Okay, actually, this is quite easy to compute even without that. Okay, but it's more about, okay, if I want to compute the one for stats fast, I already have the numbers plugged in. So the sum of D is -20. Oh, that's easy to compute. Sum of D squared is 112. So D bar is -3.33333. Standard deviation is 3.01109. Okay, so the claim when the 13th day of a month falls on a Friday, the numbers of hospitalization, hospital admission from motor vehicle crashes are not affected. See, this is actually a bit strange. The claim says that if it is Friday the 13th compared to other Fridays, other days it's not affected, but they are actually comparing to only one Friday prior to that. So what if I can criticize this method is not really appropriate because the claim is the numbers of hospital admissions for motor vehicle crashes are not affected. Is it due because to the Friday? Or is it due to the 13th? Or is it compared to just other day, any random day of the month? Okay, because even if you want to say, oh, compare Friday the 13th and Friday that is not the 13th, they're supposed to also take a look at the Friday the 20th, which is the week after the 13th. because it is possible that, I mean, it's common that at the beginning of the month, we tend to be happier. I mean, I know that's for sure. At the beginning of the month, we tend to be happier. Then toward the end of the month, we tend to be not as happy. Why? Well, when you get your paycheck, you tend to be happier. Okay, and during the month, even though you know you need to pay this, you need to pay that, but toward the middle of the month, when you, after you start paying this, after you paying that, then you start realizing, oh, you know what, my money is depleting. Then we start having less focus when we drive. It could be, you know, I make up stories, you know, I make up stories, but I don't think this is an appropriate way to look at that. Okay, especially the claim seems to single out Friday the 13th compared to other days, right? Not affected, not affected compared to what? Compared to Friday the 6th? They're supposed to be specific compared to the 6th, Friday the 6th, or Friday prior to that. Okay, well, anyway, let's see. Hypothesis. This is what I meant by they claim one thing, but the data is a different thing. Okay. Yeah, what they do and what they say are different. So mu1 is not is equal to mu2. So mu1 not equal to mu2. So mu d not equals to 0. Mu d equals to 0. The claim is here, and that's a two-tail again. It's not always two-tailed though, but in these three examples we have today, happens to be both of them two-tails. And then test statistic. T equals to negative 3.33333 minus 0 over 3.01109 over square root of 6. I will just use calculator hypothesis test right away, but I need to fix the number a bit. So this one here, I need to use negative 3.12345 and then this is 3.10, I'm sorry, 0.011109. Sample size is 6. Two-tail test, calculate, done. No, this is one for stats. No, what I want is t-test. What happened? I need to fix this 0.34, negative 3.33333, and this one is 3.01109. Yeah, 01109. Okay, this is the one I need. These are the number I'm supposed to get. Let me check using calculator. Negative 3.33333 divided by the parenthesis of 3.01109 divided by square root of 6. Negative 2.71163. Negative 2.71163. Oh, it matched with this. Now then, p-value. It's two-tail test. It's negative 2.71163, but I need to double it. So 2 times TCDF, negative E 99, negative 2.71163, degree freedom 5. So that's 2 times TCDF, negative E 99 to negative 2.71163, degree of freedom 5. Positive 0.02110. 0.02110. Okay, now then multiply that by 2, 0.04219. Which is the same to what we have here. Yeah, happy. Then I can safely go on. The alpha is 5%, so we will reject null hypothesis. Reject null hypothesis. And step 6, conclusion. At alpha 0.05, there is, well, the null hypothesis, the claim goes to the null hypothesis. So now we do have enough evidence, okay, to reject. Okay, there is sufficient evidence or enough evidence to reject the claim. That let me quote this, when the 13th day of a month falls on a Friday, the number of hospital admissions is not affected. Okay, that's for 9.3. Now we will go on to hypothesis testing for two population proportions. So 9.1, hypothesis test on two population proportions. Let's see the modification. In the step 2 on the hypothesis, we will be comparing two population proportions. And you adjust that with the null hypothesis. And we need to modify it such that we have constant on the other side. And that is by subtracting by P2. Okay, for test statistic, we will use Z. For every proportion hypothesis test on proportion, we will use standard normal distribution. That's Z equals to P1 hat minus P2 hat minus P1 minus P2 over, now this one, the bottom one is long, square root of P bar Q bar over N1 plus P bar Q bar over M2, where P bar is the sum of the number of successes or desired result over the total sample of those two. So later on, the informations we get will be the following. We have data number 1, data set number 1, data set number 2. You have N1, X1, N2, X2. Now what you need to do is to find what is P1 hat, what is P2 hat, and what is the P bar. Okay, that's what you will do later. Now, with that said, let me ask you, together with our break, let me ask you to try doing this one, only to do the setup, okay, for number 9. Amongst 198 smokers who underwent a sustained care program, so sustained care program, that's the sample size, 198. Now, 51 were no longer smoking after 6 months. Now, the regular care, the sample size is 199. Now, 30 of them no longer smoking after 6 months. Okay, we will do the hypothesis test after the break, but I need you to do, during the break, I would like you to do P1 bar, P2 bar, I'm sorry, P1 hat, P2 hat, and P bar. Okay, I want you to do that first. That should take you only a couple minutes plus your break. We come back at 11:20. You know what? Let's just do a long break up to 11:35. So 11:35, you are done with this. 11:35, you are done with this. Now, I will teach you how to use calculator to compute those 3 numbers. You can compute it as usual though. So for example, let's see. So P1 hat is 51 over 198, right? That's 51 over 198. That's 0.257575. So that's 8. Well, P2 hat will be 30 over 199. That's 30 over 199. That's 0.15075. So P bar will be 51 plus 30 over 198 plus 199. That's 81 over 397. That's 0.20403. Okay, now if you use calculator, you will use stat test 2 proportion C test. Number 6, 2 proportion C test. The proportion always C test. Proportion always C test. Okay. Now then, x1 is 51. N1 is 198. X2 is 30. N2 is 199. And later on, we will test the claim that its smoking cessation is greater than sustained care program. Hold on. Oh, it's greater with sustained care program. Okay, so step 1, the claim. I need to set up the step 2 first, and then I know which tail I'm doing that. The claim is the rate of success for smoking cessation, stop smoking, is greater with the sustained care program. So hypothesis with sustained care is the success rate is higher. So that's P1 is greater than P2. Later on, we modify that to be P1 minus P2 is greater than 0. Accordingly, null hypothesis P1 is less than equals to P2. The modified version will be P1 minus P2 is less than equals to 0. This is the claim, and that's a right tail. Okay, step 3, test statistic. Okay, let's go back to my calculator first. So this is a right tail. That's a right tail. Calculate. So from here, later on, you see I get my test statistic, p-value, and actually, you see that we have p1. This is my p1, p2, p bar. Do you see that? Now then, my test statistic that will be z equals to p1 hat, which is, so I still need to pretend that I write it down. Okay, p1 hat 0.25758 minus 0.15075 minus 0 over square root of P bar 0.20403. Q bar is 1 minus that. Let me write it down. Q bar is 1 minus P bar, which is 0.79597. Over 198 for the first group plus copy paste the numerator of the P bar Q bar for P bar Q bar over 199. And that will give us 2.64076 as seen here. Okay, actually, because we did some rounding, not exactly the same number with a P1 hat, P2 hat, and P bar. So the number actually not precisely this, not precisely this. Now the thing is to punch this number in, it's quite tedious. Okay, let's see. So that's parenthesis 0.25758 minus 0.15075 minus divided by, close parenthesis divided by the square root of 0.20403 times 0.79597 over 198 plus The second term of that radical will be 0.20403 times 0.79597 over 199. So this is the actual number. 640 what? 96. Yeah, but you see that the error is on the third or maybe on the fourth or on the third decimal place, okay, such that the p-value later on will not be affected that much. So when we do our p-value, there will be right tail, that's 2.6476076. So p-value equals to normal CDF to 2.64076 to E9901, and that should give us 0.00414. Now, if I use the real number, if I actually compute this with the rounding to 5 decimal place, I get this thing, right? Now, suppose I use that 2.64 something. So the p-value, normal CDF, 2.64096 to E9901. Let's see what's the p-value. So Thomas, in the real test later on, which method you want me to, which number you want me to give? Either one, but just be consistent. Just be consistent. Okay, just be consistent. So this will be normal CDF. Oops, not that one. Normal CDF. 2.64096. Delete that. And then E99, let me make it big number. Okay, I get 0.00413. 0.00413. So we have some difference, but the difference is so small. Okay, I know when I do the grading, I know which one I want to see. For sure, I want to see this. Okay, you better give me this thing. Okay, you better give me this thing. Okay, now the one here, either you get this one. If you give me this, I know you use calculator to compute that using the two proportion C test. If you give me this, I know you actually compute from here. Okay, now if you give me, if you use this number here, of course, you still write this, right? If you use this number, then you're supposed to give me something like that. If you use this number, you're supposed to give me something like this. So what I don't want to happen is, you use this number, but you give me this p-value. That's wrong, of course. Okay, or you use this, but then this is your p-value. That's also wrong. Okay, be consistent. Be consistent. Be consistent. If you use the result from that the two proportion C test, then give me the result from there also. Okay, now anyway, from here we see that because the p-value is less than 5%, as I know, they want 5%, right? Oh, 1%. 1%. So alpha 1%. It's still less than 1%. So informal conclusion. Reject null hypothesis. And conclusion. At alpha 0.01, there is sufficient evidence to support the claim that, and we support this claim, right? Let me just quote it. And copy paste. Okay, now how about the critical value? The same thing. We use C-score. That's a right tail test, is it right? Yeah, right tail test. So this is the critical value such that the area on that right tail is 1%. So the area to the left is 99%. So C critical is inverse norm 0.9901. That will be 2.32635. Is it right? Let me check. Yeah, that's the number. Okay, let me go on. Number 19, we have two more problems, example I want to go over, but I believe even in my lecture video, I already did enough. I have done enough examples for you to just go on with practice yourself. Okay, now you will see that I kind of rush because I want to cover one test for you, sample test 4 for you. Okay, I already have sample tests that I went over with my Monday, Wednesday class at West LA College, and I am currently posting the video, the recording on YouTube that I will show you later on in the announcement. Of course, I will post that on the announcement. Yes, my purpose is I go faster right now so that I have more time later on. Okay, let's see. Number 19, in a study of treatments for very painful cluster headache, so only for cluster headaches, 150 patients were treated with oxygen and 148 other patients were given placebo. Okay, so let's say for the first group is oxygen group and the other one is placebo. First group, sample size 150. The second group, 148. And among the 150 patients in the oxygen treatment group, 116 of them free from headache in 15 minutes after treatment. Among the placebo one, 29. Oh, seems like it makes a very big difference, huh? Okay, we want to use 1% significant level to test the claim that oxygen treatment is effective. So step 1, claim oxygen treatment is effective. Step 2, hypothesis. So we want to show that P1 is greater than P2, the success rate, the recovery. Okay, the treatment is more effective, right? So P1, those people who recover free from headache after 15 minutes of treatment is more. Okay, this one is P1 less than equals to P2. Now modify so that we have constant on the other side. This is the claim, and that's right tail. Okay, now let me use calculator to speed up my computation, my work. Okay, so I go to test to proportion C test. Oops. To proportion C test. Successes in the first group 116 out of 150 people. Successes in the second group 29 out of 148 people. And we are testing right tail. Calculate. Ding. So we have this number now. Okay, now then, when I do my test statistic, again, you need to pretend that you get the number, right? Okay, let me move this down a little bit. So I will say, oh, P1 hat is 116 over 150. That is equals to 0.77333. P2 hat is 29 over 148. That will be 0.19595. P bar is 0.48658. Therefore, Q bar is 1 minus that. Is 0.51342. Now then the C score, the test statistic will be 0.77333 minus 0.19595 minus 0, big over, this one is long, square root of 0.48658 times 0.51342 over 150 plus 0.48658, 0.51342 over 148. And when I look at that screen, I see, oh, the C score is 9 point something. So this will be 9.97062. And then the P value, that's a right tail. 9 point something. P value is normal CDF 9.9762062 E9901. That's practically 0. Why? Because that's 1.0448 times 10 to the negative 23. Right? So that's practically 0. Okay, always give me the decimal rounded to 5 decimal places. Okay, not just the scientific notation, the 10 to the negative 23. No, I need you to write it down. What is that in 5 decimal places? Okay. And then step 5, informal conclusion, reject null hypothesis. And then step 6, conclusion. What is the alpha? 1%. At alpha equals to 0.01. There is sufficient evidence to support the claim that oxygen therapy is effective. For extra credit, 4B, critical value, that's a right tail. Area there is 1%. So the area to the left is 99%. C critical is inverse norm, area to the left 99%. Mean 0, standard deviation 1, because that's standard normal. So this is 2.32635. Number 22. In a random sample of males, it was found that 23 write with their left hands and 217 do not. Okay, so among males, the sample size is 23 plus 217, right? Okay, though there are 23 left hand, 217 not. Okay, of those, 23 left hand. Among females, there are 65 with left hand, 455 not. So this will be 520. The alpha is 0.01. Test the claim that the rate of left-handedness among males is less than that among females. The rate of left-handedness among males is less than that among females. Okay, now again, this is something they claim. What they claim and what they actually observe are actually related, but not always true. Okay, very likely the person who did this actually, so the person who did this research was not aware that because of culture, it is possible somebody is left-handed, yet he still write using right hand. Okay, I am for one. I'm actually a left-hand person. Okay, I'm a lefty. However, I write using right hand. Why? Based on the culture where I grew up from, like I came from Indonesia, where Muslim tradition is very strong in a positive way, very strong in our culture. Okay, and also not only Muslim culture though, Asian culture in general, we see left hand as something not appropriate. Okay, such that even though I originally wrote using left hand, my parents insist that I need to change to right hand. So I actually learned to write using right hand, even though I'm a left-handed. Okay, now the thing is then, if he or she, in this case, Miss Elaine Costas, only judge or only see that somebody's left hand must write using left hand, then there's a little bias there. Okay. Now, of course, as long as he observed only those people without that interference of culture, where because they are left hand, I mean, they are left hand, but because they come from certain culture, they end up writing using right hand. If we can actually avoid such kind of distortion, then this will be a good way to look at that. Okay, so I prefer to say the rate of left hand writing among males. So be specific with the writing. Okay, left hand writing among males is less than that among females. Okay, and how about those people who ambidextrous? Okay, from the wording seems like this person actually avoid ambidextrous, because when he say 23 write with their left hand, 217 do not. So that's how she avoid ambidextrous case, right? Okay, somebody who can write using left hand and right hand, right? But still, I disagree with saying that somebody is left hand simply because he writes using left hand. Because I have seen enough. Most Indonesians that I know, at least Indonesians that I know that are left-handed, most of them actually write using right hand. It's, let me tell you how bad it is in Indonesian culture to write using left hand. It's to the point that when I was still in kindergarten, when I learned to write, okay, my mom actually tied my left hand to the chair. My parents tied my left hand to the chair, such that I can only use my right hand for my activity at the table. Okay, I remember that very, very well. There was one time they tied me to a chair, and then they need to go out for like a couple minutes, maybe like around 15 minutes. And during that time, I happened to be alone at home. Now in Indonesia, that's fine. Okay, but then I need to go to restroom. So I basically drag with me the chair to go to restroom. Yeah, I need to drag the chair together with me to go to restroom, and it's very difficult, very difficult. You know, like I was like in 5 or 6 years old at that time, and still learning with my motoric skill. Okay, with one hand being tied, and the chair happened to be quite heavy. It was actually I really fight hard just to get to the restroom. Okay. So that's why I remember that very well. What now you can call that child abuse here, but in Indonesia they call that education. Okay, and if people ask me, Thomas, so do you regret that happened, that was done on you? No, I'm actually fine. In fact, in some sense, I'm actually happy that with my parents train my right hand, insist to train my right hand. Right now, my right hand can be more active compared to my other peers who write using left hand. So they write using left hand, their right hand already passive and becomes even more passive. My left hand is dominant, but I still can use my right hand to write. So my motoric skill, right hand motoric skill, is actually better developed compared to my friends who are left-handed and writing using left hand. You see what I mean? Okay. So in some sense, put it this way. Of course, in America, I drive. Now, in America, our steering wheel is on the left. Okay. But in Indonesia, I never tried this, but I believe, I have confidence in Indonesia, the steering wheel is on the right-hand side. And I believe I can easily adjust, not right away, of course, I still need to practice, but I can easily adjust if I suddenly need to drive there. Okay, that's one little example, okay, based on the culture. But let's understand that In this case here, what the author of that research claim that the left-handedness among males is less than that among female should not be judged or be observed only from what hand they use when they write. Okay, it's more than that though. It's more than that. I put it this way, in the nasty way of putting it. Okay, I write using right hand, but if I punch somebody, I punch using left hand. I write using right hand, and at the same time, I can punch somebody else using my left hand. You know, other people, they write using right hand, but for them to punch, they need to put down their pencil first and then punch somebody and come back, right? Okay, no, I can do both things at once. You know, okay, yeah, but yeah, it has some cultural background for that. Step 2, the hypothesis. We want to show the claim, try to show that rate of left-handedness among males is less than among females. So P1 is less than P2. If the males one is considered the first group, so P1 is less than P2, and to modify that, P1 minus P2 is less than 0. So this is H0, P1 greater equals to P2, H0, P1 minus P2 is greater equals to 0. The claim is with the alternate hypothesis, and that's a left tail. Okay, let's get calculator, plug in numbers. So stats, test, 2 proportion C test, X1, that's 240. Oh, I'm sorry, X1 is 23, and 1 is 240. X2 is 65, and 2 is 520. And we will do a left tail test, calculate. Oh, by the way, I need to clarify that even though I'm glad that my parents trained me to use my right hand to write, therefore my right hand is not as passive as plenty of my friends who are left-handed. But I'm still glad that in America, there's no different treatment between people who are left-hand and right-hand. Seriously. The treatment of using left hand in Indonesia, at least, is to the point that they don't say it out explicitly, but it's to the point that if you use left hand, you are considered strange. It's like the level of surprise that I write that I'm a left-handed in Indonesia is much higher compared to the level of surprise when I say to other people, oh, I'm left-handed. In fact, at one point, I asked around, I found out that around 10 to 15% of our students actually left-handed. So you know, because it's more than 5%, it's not considered rare, right? It's not considered unusual. I mean, yeah, of course, 10, 15% is not majority, but you cannot say that they are not, they're unusual. It's still possible, right? Now, back in Indonesia, it is less than 5%, okay? Because of the influence of culture. Now, here we see, let me drag it down. Here we see P1 head is 0.09583. P2 head is 0.125. And P bar is 23 plus 65 over 240 plus 520. That's 88 over 760, that's 0.11579. Therefore, the Q bar is 1 minus that, 0.88421. Now, I wonder if I ever share that with you. Thomas, how can you subtract 0.11579 by just from 1 by just looking at that? The way I do it is actually like this. Okay? I think of what number make it 9 here. What make it 9? What make it 9? What make it 9? What make it 9? What make it 10 for the last one? Okay, because when you subtract 1 minus that, 1 minus 0.11579, when you subtract, the procedure was you do borrowing all the way, right? So this becomes 10, but this is 9, this is 9, this is 9, this is 9. You see what I mean? When you subtract. Okay, so what is 9 minus 1? What number plus 1 give you 9? 8, and then 8, and then 4, and then 2. What makes it 10 for the last one? 1. That's how I did it. Okay, but if you never really do this subtraction by hand, it's of course this is not arithmetic class, then you will never understand what I did. Right? Okay, just like if you never go through the pain of studying, then you will never appreciate your diploma. Test Statistic. Z equals to P1 hat, which is P1 hat 0.09583 minus 0.125 minus 0 over square root of P bar. 0.11579 times 0.88421 over 240 plus 0.11579 times 0.88421 over 520. And this, according to my calculator, will give me negative 1.16809. So I get this number from here. Okay, and then P value. That's a left tail, negative 1.16809. So P value is normal CDF, negative E99, negative 1.16809, 01. That should be 0.12139. I get it from here. Okay, then step 5, it's greater than alpha. I think the alpha is 5%. No, 1%. Okay. Informal conclusion. Even though the sample proportion shows so, but it is not significant enough to the point of us rejecting null hypothesis. So the conclusion, at 1% significance level, there is insufficient evidence or you can also say there is not enough evidence to support the claim that let me copy paste. Yeah, the rate of left-handedness among males is less than that of among females. No, it is not true, at least from the writing point of view. Okay, the sample proportion seems to be less than, but the difference is not significant enough to support that the proportion of the populations will be so. Okay, now your test 4 will be up to chapter 9. Your test 4 will be chapter 8 and chapter 9. For the next 1 hour only, unfortunately, I will try to do as much as possible from winter 21. Test 4 from winter 21. Let me see, where's my file? From winter 21. Your test next week will be for 3 hours. You will start from 8 something, from 8:20 until 11:20, and then we take a break. Instead of only 2 hours, you will have 3 hours. Okay, you will have 3 hours for a test because there are a lot of writing, right? I understand there are a lot of writing. That's why I give you more time. Then after that, we will have a half an hour break before then I go over some linear regression discussion on linear regression. So this is winter 2021. Give me a second.